And then the next speaker is Jana Guenther. And she will tell us about the equation of state at finite density using resumation techniques.
Yes, can you see my slides in full screen? Does that work? Okay.
It's fine, I see it.
Okay, great. Okay, first let me thank the organizers, especially Maria, for the opportunity to talk about our most recent paper on the equation of state. We started already a little bit discussion about that after Claudia's talk, so also my thanks for Claudia for the nice introduction. So let me jump right in with the outline of my talk. I will give you a little bit of motivation and an explanation what we're doing with analytic continuation. Then I will try to explain the analysis techniques we used in some detail. And of course, the most important parts are our results on the equation of state with strangeness neutrality. And I won't stop there, but I will also go a little bit in our efforts to go beyond strangeness neutrality. So Claudia already mentioned the infamous sign problem, which is the reason why Lattice QCD has such a huge challenge with covering finite density in the phase diagram. Here are the rather easier formulas for, to explain this. When we calculate the QCD partition function, we have these integrals over the quarks, which are just roughly denoted by this psi and psi bar here, and over the gluons or gauge fields denoted by U. These psi's are Grassmann variables, so they're not suited to numerical integration. That's no problem at all. We can just do this integral analytically, and then we have the determinant, which depends on the gauge fields. And then we can use this colored part, green and blue, as our Boltzmann weight and do a numeric Monte Carlo integral to calculate the partition function. However, for this to be a proper probability weight, it has to be a positive number. This only is the case if we have particle-antiparticle symmetry. So if we introduce real chemical potential, this determinant becomes complex, and a complex number is not a very useful probability. So then we can't do Monte Carlo integrals anymore. And this is the reason why it's so difficult to get information on the phase diagram from Lattice QCD. There are lots of techniques around to deal with that. At the moment, my personal two favorites are the sign reweighting and the complex Langevin, though that might change at some point. But for now, if we want to have results that are continuum extrapolated, have decent decently small quark masses and a reasonable volume, we are limited to techniques that rely on somehow extrapolating either by the Taylor expansion or another expansion technique from zero chemical potential, or what we are doing within the Wuppertal-Budapest collaboration most of the time from imaginary chemical potential. So how does that work? I put a phase diagram here that looks a little bit different than the ones that Tatjana and Claudia showed in the previous talks, because here we have the chemical potential squared on the x-axis. And this means that here we have a purely imaginary chemical potential, and in this area we can actually do lattice simulation. Of course, this is unphysical. In the real world, there is no imaginary chemical potential, but that's not a problem for us. We can just do our simulations there. And then we know that at zero chemical potential, the transition is a crossover. So it's described by an analytic function. And as long as this function is analytic, we can just take data points, for example, here for the crossover temperature, and fit some functions through this data point and extrapolate to real chemical potential. Another way, here it was a transition temperature, is to just look, for example, at fluctuations at a fixed temperature and extrapolate those. With our data and different fit function, we get plots like this. So again, here is the 0, and there is a mu squared of the chemical potential here at this axis. So we have data here, and we can use different fit functions. The use of different fit function is necessary because they might give you quite different results, even if they all look fine in the realm where we have data. Okay, that's the idea of our analysis. So what was the trouble with the equation of state? That was also what was a discussion after Claudia's talk with Friedloff was about. If, for example, one takes the baryon density and uses the Taylor expansion with increasing coefficients, then at some point we see such wiggles. Of course, if we do know the fluctuation with more precision, this wiggles might go down. But if Friedloff pointed out, at the very least, if we go to infinite chemical potential, there will be very weird things happening. And to us, it seems like in this area, there is some behavior that we're not exactly looking for. That's also our explanation for this huge error bar here in this plot. We actually looked at that with a very simple model where there is no arrow at all. And still here, if your mu b is chosen high enough, you see some kind of plateau in the baryon density. And if you take the next order, it actually becomes somewhat worse. So as long as you take your error into account properly, like it's done here, this is not really a problem in the sense that, of course, there is room for an equation of state where everything is rising monotonically. It can become a problem, as Claudia experienced, if you just take the central value and try to plug that in some model. Then from such a plateau of the central value, even though it's not the case within the arrows, you might get unexpected behavior. So the idea is maybe we can use a different expansion scheme that maybe we even have a chance to reduce our error. That would be great. So we noticed some behavior in our imaginary chemical potential data. And this is from our paper of last year, where we did our simulations with vanishing strangeness potential. But we noticed that with a very simple rescaling, our curves for certain observables just collapse on each other. And this was the basis to construct an expansion scheme or analysis scheme, which uses these collapsing of the curves. And then we can have an equation of state where also the central value does not show any plateauing behavior because higher order terms are taken into account a little bit differently. Okay, so how does this analysis work? Especially now we want to go to strangeness neutrality. That was our paper from last month, not last year. And we're using the condition that the charge chemical potential is 0 and the strangeness density vanishes. This results in the derivative of the strange chemical potential, which can be noted by these fluctuations here. And it also means that every time we want to take a derivative now in comparison to what we did before without any strangeness, strangeness chemical potential, the total derivative with respect to the baryon chemical potential now gets a second term, which is exactly denoted by this total derivative of the chemical potentials here. And using this, we can write the derivatives of the pressure. We call them here C, B, and then the number of which derivative we want. And starting again with the net baryon density, so this would be CB1, we actually notice we have the chi1b here, and then we get this extra term. However, since we want strangeness neutrality, this term actually vanishes because this quantity is 0, and then we just have chi b1 again. However, if we take now higher order derivatives, we have to keep in mind that this term might also contribute in some way. Okay, first we check if for our simulation result at strangeness neutrality, this rescaling still works, and that looks rather good, especially for the lower temperatures. These curves collapse nicely. However, here at higher temperature, you see that it doesn't work as well anymore. And it's very clear that this rescaling scheme will break down at very large temperatures. However, this can actually be remedied by rescaling everything with its Stefan-Boltzmann limit. And if we do that with our data, it's only a slight change, then at least we know that it doesn't necessarily have to fail at high temperatures, and our curves are still somewhat collapsing. Okay, now we want to calculate this shift and also the correction to this shift. First, I should briefly address why we think this rescaling works. Well, we started with an observation that it works. I showed you the plot. But an idea is that it could be ultimately related to the critical scaling in the chiral limit. So if you look at the Columbia plot and you send your light quark masses to 0, there could be a critical region. And if the universal contribution to the equation of state is large, this would mean we could describe everything with a single scaling variable, which would then depend on the temperature, the quark masses, and the chemical potential. And if the strength of the transition is strongly influenced by the light quark masses, our curves could actually keep their shape, and that is what we see approximately. That also fits with the observation from a previous paper, which Claudia also already showed, that the width of the transition approximately remains constant. This, of course, is not a proof that this is the case, but to us it seemed like a logical explanation. Okay. So what do we do to measure this shift? We start with our data at 0 chemical potential. We spline this data, and then we look at our data at imaginary chemical potential. In this plot, I will only show 2. We have several others, but this plot should not be too crowded. We also spline this data. And then we measure the difference between these 2 curves, which is basically the shift we want to. We then calculate this quantity pi, we call it pi for proxy, which is the difference in temperature between these 2 curves normalized by the temperature and the chemical potential. And from this, we will later on calculate our expansion. I also want to say that the splining of the finite new data is only necessary because we want to do a continuum limit later. So we need this exactly at the same temperatures, these differences. We could avoid that if we stick to a single lattice spacing like here in the plot. But since we will need it later on, we decided to already spline at this point, and we can do it for another chemical potential. And again, we measure this difference here and calculate our proxy pi. The lattice setup we are using is the following. We have our standard action in this collaboration where we use a tree-level semantic improved gauge action with 4 times Staudt-Smearts-Degard fermions. We have our simulations with 2 + 1 + 1 flavor on a line of constant physics that is set with pion and kaon mass and a fixed ratio between strange and charm quark. We do our simulation at vanishing strangeness. We actually tuned our simulation that this holds rather well. And we do a continuum estimate from 4 lattice sizes, starting with n-tau 8 up to n-tau 16. We have various values for the chemical, imaginary chemical potential. This 5.5 here is in brackets because this data is only available to us right now at n-tau = 12 lattices, but there we can use it. We will also include in our systematic error later on our scale setting by doing it with two methods, one from fpi and one from W0s. All our lattices have a decently sized volume. On the topic of systematic error, what do we include in that for this analysis? Well, I already mentioned we use two different splines, and we use three different sets of node points for the spline for the mu b equals 0 data, and two different sets for the finite imaginary mu b. I also already mentioned the scale setting. Then when we do our fit in the direction of the chemical potential, we use two ranges. We cut it off. And we also use two functions for the chemical potential dependence of our global fit, which I will introduce in a moment, either a linear or a parabola. And we either include or exclude our coarsest lattice in the continuum extrapolation. This in total leads us to 96 fits, which we weigh uniformly with a cutoff in the Q value of 1%. So if a fit really doesn't fit our data, we throw it out. Otherwise, we just keep it and weigh everything uniformly. Yeah, like I said, we work now with this proxy quantity pi, which we rewrite in terms of some expansion coefficients. We call them lambda here. We call them kappa if we do not divide by the Stefan-Boltzmann limit, to distinguish that in the different papers. And here we also include in a global fit the continuum dependence. Later on, to calculate different thermodynamic quantities, we will need a temperature derivative of these expansion coefficients lambda. That's why we also do a fit to them to do this temperature derivative. And on the left-hand side, we can actually constrain this fit with HRG data. Here in this formula, you see this generic A instead of the lambda BB for the baryon density, which is used here. The reason for that is that there will be different quantities, which also include some strangeness that I will discuss a bit later in this talk. Okay, let's go to the results we can obtain. So I already promised we need some thermodynamics. So to get the pressure, we have to integrate our baryon density, where we can rewrite the dependence of the chemical potential like this. And we take our pressure at 0 chemical potential, actually from a rather old work from 2013. We then also calculate other quantities, for example, the entropy density S. When we do calculations like that, we always need temperature derivatives. And there one has to be a little bit careful with our data, because if you look in the thermodynamic books, they always want derivatives, or quite often want derivatives, where the baryon chemical potential is held constant. However, what we can do if we fit our data into a derivative, we will have fits or derivatives where the chemical potential divided by the temperature is constant. This produces an extra term of which one has to take care in this analysis. Also, we want to stay on the strangeness neutral line, which means that we do our derivative of the pressure with respect to temperature. Again, the strangeness neutrality will eliminate one term, which makes the total and the partial derivative the same. And with that information, we can rewrite our temperature derivative, and then actually this expansion coefficients I calculated before show up in this formula. And here we also need their temperature derivatives. So we have this formula, and from that we can actually calculate all the other quantities we need. I already talked about the energy density and the entropy. Our results plots then look like this. We can go up to baryon chemical potential over T up to 3.5 without having enormous arrows, at least for most of our temperature range, and also without seeing any surprising behavior on the central value, that our arrows become large here at high temperature is related to the fact that there our shift becomes extremely small, and then it becomes difficult to calculate this accurately. If we calculate the pressure, the nice thing is the arrows look much smaller. This is basically just due to the fact that we add a large number. So actually, this is a more precisely known quantity, even though it doesn't look like in these plots. And as shown before, we can also calculate other thermodynamic quantities. So, as promised in the beginning, we also want to see what happens a little bit away from the strangeness neutral line. In heavy ion collision experiments, Claudia already brought up the point that this is not always everything homogeneous, and there might be pockets of gluon plasma where there is some net strangeness, even though the total strangeness is 0. And to look a little bit away from the strangeness neutral line, we look at 2 other observables for which we can also use some rescaling. One is the ratio between the strangeness and baryon chemical potential, and then the second order strange fluctuations.
5 minutes.
We do the exact same analysis than before and end up with now 2 other lambda coefficients. So now we have BS for the ratio between strange and baryon chemical potential, and 2S for the second order strange fluctuations. Again, we fit them to get a temperature derivative. And how can we use that now? Well, if we want to shift our strangeness chemical potential away from the strangeness neutral line, we can do an expansion of both the strangeness and the baryon density. We only keep terms for now which are linear in the delta mu s. And then we will express everything in the ratio between those 2 quantities, which we call R now. To avoid confusion, sometimes the R has been used for the ratio between charge and baryon number, but here it's strange and baryon number. If we invert this relation, we actually can write this delta mu s as a function of R. And then we can calculate that by plugging in our results for the different quantities. What you see here from the hadron resonance gas, the dashed line is actually also truncated at linear order in the delta mu s. So this gives us some idea of how much we are missing if you look at the difference between the 2 hadron resonance gas lines. And yeah, these are the different delta mu s we get for different R values. Then again, we can calculate the baryon number density. This can be expanded in R. And then here, compared to our strangeness neutral results for mu b over t equals 2, we can show here what happens if we introduce some strangeness away from that. If we want to look at the pressure, we actually do not plot the pressure directly, but we observe that if we do the expansion in R, the leading order term, actually the linear term, vanishes. So we start with the quadratic term in R, and this can be easily be written out in terms of the baryon density and the second derivative with respect to strange chemical potential. And this is the coefficient we plot here for different values of the baryon chemical potential, again, with comparison to the hadron resonance gas. And this one can then easily use to calculate the pressure away from the strangeness neutral line. So let me summarize. The basic idea for our analysis was that we can rescale different observables in a way that they nearly collapse. I showed you how we then use this observation to fit the differences in the temperature, calculate our expansion coefficients, and then use that to calculate various thermodynamic quantities. And then we go the step away from the strangeness neutral line by adding also strange observables. And this was the second to last plot I show you. So the baryon density at various values of our R coefficient. So thank you for your attention.
Thank you very much, Jana. Do we have questions? While I don't see any, I will ask one myself. Your rescaling, how do I really interpret this? This means that, so the fact that it works means that you have a low order polynomial dependence on mu, right? That's what follows more or less.
Yes. So if it works perfectly, then actually, so if this would be perfect, then everything could be described with this 1 lambda coefficient. Right. Of course, it's not perfect, as you can see in this rescaled plot. So we get corrections for that, which we then denoted by lambda 2 and lambda 4. So lambda 4 would be the correction. And the better this works, the smaller our lambda 4 will be.
Right. Okay. Fridtjof?
Yeah, maybe a little bit along this line. So I also recognize that you now talk about rescaling rather than resummation, which was a word used in earlier days. Is it correct that all your analytic continuation is based on a 6-order polynomial? And
no, it's not. Okay, yes, we have. Where did I write it out? We have here our up to 6-order polynomial, but that's not the same as if you would just use the chi-b up to 6 order. So due to this rescaling and shifting, this is a little bit different in the higher order terms, which I think justifies the term resummation, because it's a different sum than the standard Taylor expansion.
Well, I guess my question would be, if you go, I don't know, this 6 order is maybe not the same as in the Taylor series.
Yes.
That you use for extrapolation. But my question is, if the Taylor series has a certain radius of convergence, what would be the radius of convergence of this rescaled scheme?
Okay. Let me think about that a moment so I don't say anything wrong. My first guess would be that it should not change it, since it's also a shift away from the zero chemical potential, from the zero chemical potential curve. So I don't think it would influence the radius of convergence.
Which I guess would mean when you become sensitive in your original scheme, where you actually were sensitive up to a 6-order expansion coefficient in the series. When you become sensitive to 8th and 10th order, then presumably you would not gain from this rescaling scheme?
Probably not as much anymore. So the basic idea is that we reorder our summation in a way that these 4th and 6th order are relatively small, and hopefully even the higher orders, so that the main part is shifted to this first order coefficient. So if you have now a Taylor series with lots of higher coefficients, that in my point of view should be as good or even better. But as long as they are so difficult to obtain, we tried to rewrite it in a different way.
Okay, thank you.
Okay, is this a question or no? Then I don't see any further questions right now. Then we thank Jana once more. Thank you.